In this second video for section 4.3, we're going to look at an example where we need to model exponential decay instead of exponential growth like we saw in the first video. Here's the setup for the example. You decide to make ice in your freezer using an ice tray. Your water starts at 72 degrees Fahrenheit, so that's room temperature straight from the tap. And your freezer maintains a constant temperature of 5 degrees Fahrenheit. And then what you do is, over time, take measurements of the temperature in the ice tray. And this data is collected in a table. On the first row, we have time in minutes. And on the second row, we've measured the difference in temperature between the ice and the temperature of the freezer. So as you read this data, it's important to keep in mind that this is not the temperature of the ice, or the temperature of the ice tray. This is the difference in the temperatures between the water in the ice tray and the freezer. So when the ice tray goes into the freezer, there's a 67-degree difference because your water is 72 degrees Fahrenheit and the temperature is 5 degrees Fahrenheit. And when you subtract those two numbers, you get 67. And then each minute you measure this difference again. So after 1 minute, the difference has gone down to 64.3, and then you can read the rest of these numbers. One thing that you'll want to notice about this data is that the changes minute to minute are not constant. So the change from 67 to 64.3 is not the same as the change from 64.3 to 61.7. This is a change of 2.7, and this is a change of 2.6. So what we're going to check is the ratios of the temperature from minute to minute. So in this new table, on the first row I have the change in time, and on the second row I have the temperature ratios. So for 0 to 1 minute, I have the temperature at 1 minute divided by the temperature at 0 minutes, and I get 0.96. And in this table I've rounded everything to 2 decimal places. And then you'll do the rest of the changes from 1 to 2. You'll have 61.7 divided by 64.3, and then continue. And for each ratio, you're going to get the same number, 0.96. So what this means is that the temperature of the water, the temperature difference of the water, changes by a constant multiple for each minute. For each minute, you multiply by 0.96 to get the temperature difference for the next minute. That means the temperature difference follows an exponential model. So we'll want to build our model, our formula. On the left side, we'll have our temperature difference, that's our function, and it's going to be equal to the initial value, that's the initial temperature difference, and then we'll have the multiplication factor, and our exponent is the number of minutes. So fill in the initial value. You can read this initial value for the temperature difference here. Fill that in. And fill in the multiplication factor that you found in the table, the 0.96. And then pick variable names. Here I've chosen D for temperature difference and T for time in minutes. Let's take a brief look at our exponential model before we move on to the other parts of the example. So I've already opened Desmos and graphed our data, and here it is in purple. We can see it's sloping gently downwards. And over the top of the data, I want to graph our exponential model. So that was d equals 67 times 0.96 to the t power. And here we graphs in blue over the top of our data. And we can see how it perfectly matches the data from our table. Our table of data had the difference in temperature between the water in our ice tray and the freezer temperature. But probably what we really want to know is the actual water temperature. Let's see if we can figure that out from what we have already. So we know the difference is going to be equal to the actual water temperature minus the freezer temperature. So this is just the difference between the water in the ice tray and the temperature of the freezer. And we've already chosen a name for the difference in our formula. It was d. Let's choose t for the variable name for water temperature. And the freezer temperature we know from the problem statement is always going to be 5 degrees Fahrenheit. So fill that in as well. And we get this little formula. The difference is equal to t minus 5. If we rearrange this, we can solve for t. So add 5 to both sides of the equation, and you'll see that t is equal to 5 plus d, the difference in temperature. We can look back to our formula for d for the difference, our exponential function, and plug it in. And finally, we get the temperature of the water in the ice tray is equal to 5 plus 67 times 0.96 to the t power. Now let's get to the reason that we put the water in the ice tray. When will the water freeze? So that means when will the water reach 32 degrees Fahrenheit? This means we have to see when our function, the t equals 5 plus 67 times 0.96 to the t power, is equal to 32. So this gives us an equation that we can solve in Desmos using the crossing graphs method. Now we'll go back to Desmos to do the crossing graphs method to solve our equation. And I still have the original graph for our difference in temperature between the water in the ice tray and the freezer. What I want to do next is graph the function t for the water temperature. So let's type that out. It's 5 plus the original temperature difference graph, or difference function. So there it is in red, and you should notice that it's pretty close to the blue graph. It's just been shifted up by 5 degrees. And we're doing the crossing graphs method where t, the function, is equal to 32. So we'll also need to graph the line y equals 32. Let's get rid of a little bit of the extra clutter so that we can see our two functions. And in the current display window, they don't cross, so we'll have to expand out our view. You can use the zoom function, or you could use the tools. So 20 minutes does not go quite far enough. Let's go to 30. And once we expand our graph, we can see where the exponential function for the temperature of our water crosses the level, the line, for 32 degrees. And that's here at this highlighted point. So after 22.264 minutes, the temperature in the ice tray is going to reach the freezing point.